Daniel Whalen, and we speak about the formation of the first quasars.
Can you hear me okay? All right, so first I want to thank the workshop organizers for this really nice opportunity to come and talk about our new rad hydra simulations of some of the earliest quasars in the universe. And let me just briefly summarize where we are. So we now have found nearly 160 quasars above redshift 6. And the current record holder is this Banyatas et al. Quasar at redshift 7.5. And an 800 million solar mass black hole. And then the Mortlock et al. Quasar, J1120, 2 billion solar masses at redshift 7.1. And so a question that's been preoccupying us for a while in the community is how these black holes could become so massive by such early epochs in the universe. So there are currently two main proposed pathways for the formation of these earliest quasars. So the pathway on the left is what I would call the conventional Hop3 star black hole channel. And that's where you get a population 3 star, which are thought to be predominantly mass heavy. And they collapse to black holes that are either a few tens of solar masses to a couple of hundreds of solar masses. And then those black holes have to accrete quickly to reach basically 1 billion solar masses by redshift 7. And this is something I'll come back to in just a minute. So the pathway on the right is what I would call collectively the direct collapse scenario, where here, instead of getting individual POP3 stars forming in small halos at redshift 20 to 25, you get halos that grow to larger masses without first forming stars, because they're either in close proximity to another star-forming region that sterilizes them of molecular hydrogen, which they need to form stars in the first place, or those halos are subject to these supersonic baryon streaming motions, these relative sloshing motions between baryons and dark matter that are thought to be operating in some halos at very high redshifts. And so there, the idea is that, and this is the way I think about it, a primordial halo will form a primordial star by a mass of about 10 to the 5 to 10 to the 6 solar masses, unless something prevents it from doing so. And this is because of the robustness of molecular hydrogen formation chemistry in the early universe. And so if a star forms in a halo at that mass, it will essentially destroy the halo, because it's so bright and ionizing UV, it kicks all the gas out of the halo, number one, so it evicts all the baryons. Secondly, in many cases, it will explode, and those supernova explosions will scour the halos clean of gas. So, but if a halo instead is close to other strong UV sources, or has violent gas motions, it can grow to masses of 10 to the 7 solar masses to 10 to the 8 solar masses without forming a star. And at those masses, they reach virial temperatures of 10 to the 4 Kelvin, which trigger the N=1 to N=2 transition in hydrogen. And those halos begin to atomically cool. Atomic cooling is 10 to the 4 times, 10,000 times more efficient than molecular hydrogen cooling. And the idea there is that it triggers catastrophic baryon collapse to the centers of the halos at rates of up to a few solar masses per year. And what kind of object gets built up under such inflows, I'll come back to in a moment. The idea is you build up some kind of a supermassive star that then collapses to a rather massive black hole, anywhere from a few 10 to the 4 up to a few 10 to the 5 solar masses. So a complementary scenario that can happen is the halo might be marginally enriched, say by one POP3 core collapse supernova, where it has a metallicity of maybe 10 to the -4 solar. And in that case, what you can get is global cooling within the halo that fractures the gas into lots of small pieces that form a dense nuclear cluster of stars. And in that scenario, the stars can undergo what we call runaway collisions, building up an ever more massive star until that star collapses to form a black hole. And that process is governed by how many stars can collide and build up the massive star before the first supernova in the cluster go off and start disrupting the orbits of the other stars. So that scenario is thought to produce black holes of maybe a few thousand solar masses, not 10 to the 4 to 10 to the 5 solar masses. So intermediate between the POP3 and the direct collapse scenario. So I would say right now, well, first, debate over which of these pathways actually operates or whether or not both of them operate goes on. So I would say there's a bias in the community now towards direct collapse for a couple of reasons, as being the origins of these very early supermassive black holes. And the first is, for POP3 stars, those POP3 low-mass black holes are born starving because just like I told you, the progenitor star kicks all the gas out of the halo before it collapses to a black hole. And that object is born in very low densities in which it cannot accrete gas very quickly. So later on time scales of a few tens of megayears, when cosmological flows restore gas to the halo, what then happens is X-rays from the black hole fire up, heat the gas. The gravitational potential well of the halo is so shallow that the black hole begins to disperse its own fuel supply again. So it's very difficult for these black holes to undergo what we would say conventional Eddington limit accretion continuously down to redshift 7, as they must to reach a billion solar masses by that time. And so another issue that's often overlooked is for the lower mass black holes, say a few tens of solar masses, they're often ejected from their own host halos because of asymmetries in the core collapse supernova engine that create them. And they get kicked down to the halos at several hundred kilometers per second, and they're exiled to the voids in between the filaments typically in the halos. And so, and they're therefore ejected from their own fuel supply, so they can't grow very quickly. Now, some of these difficulties could be bypassed by so-called super Eddington or hyper Eddington accretion, where we get these fat disk or Polish donut type accretion scenarios onto the black hole, where you get a so-called advection-dominated accretion flows. And so even if you're accreting at 100 L Eddington, you only have to have a duty factor of 1% to reach 10 to the 9 solar masses by redshift 7. So that could work, but the thing to keep in mind is that primordial environments are very inhospitable in general to the rapid growth of black holes because the stars and the black holes, they just kick gas away from every place. So there's a new paper based on the Renaissance simulations where they follow 15,000 POP3 star black holes in a 40 megaparsec volume. And only one of those black holes even approaches Eddington rate accretion for some fraction of the time. And the reason for it is that those black holes and stars just clear gas out. And even if super Eddington accretion were possible, they just don't encounter enough gas to grow quickly. And that's the issue. But we don't rule it out. It's still a possibility. With direct collapse, the advantage is the black hole is born a lot more massive, so it grows a lot more quickly. It's born in much higher densities, in more massive halos that can retain the fuel supply of the black hole even when it's heated by X-rays. So typically, we think that these direct collapse objects, these larger black holes, can grow more quickly. So here, what you're going to see is the formation of a massive atomically cooled accretion disk at the center of one of these atomically cooling halos. And as you can see, at later times there is fragmentation, but these fragments tend to crash back into the central object. So instead of getting multiple, perhaps massive black hole seeds, we still get the buildup of a single, rather massive object at the center. And if we look at the accretion rates, here they are. They're typically, we see average accretion rates of anywhere from about 0.1 solar masses per year to about half a solar mass per year. And these are sustained for megayears. So the question is, what object do those flows build up? For example, do they build up a star that has a short main sequence lifetime? Or does gas just get denser and denser, higher and higher entropy until you collapse and form a black hole? And the answer is that you get a supermassive star forming. And so here, really quickly, are some evolution tracks for a supermassive primordial star. And what we predominantly find is that they're red, bloated, cool hypergiants. And that they have surface temperatures anywhere from 5,000 to 10,000 Kelvin. Those temperatures are regulated by H- opacity in the outer layers of the star. And even though they're cool and red, they become incredibly luminous. In fact, it can top out at 10 to the 10 solar luminosities by the end of their lives. So that opens the question to whether these really cool red but bright stars might be detected as the earliest stage of primordial quasar formation. And I'll come back to that in just a moment. But the other thing I want to mention really quickly is that when these stars, because they are red and cool, they're not strong sources of ionizing UV radiation. So they cannot reverse or halt or even affect the accretion that builds them up. So these supermassive stars, they're born, evolve, and die under the heavy accretion flows that create them. And the existence of that star is a tug of war between nuclear reactions at the core, which are releasing photons, extreme mass loading in the outer layers of the star due to this atomic cooling inflow, and then an attempt to thermally relax onto an equilibrium state the star can never achieve. So these stars live short lifetimes. Now, what happens is when they go above a couple of 10 to the 4 solar masses, their cores become so hot and the thermal photon densities are so high that the star can encounter what we call the general relativistic instability. And if you're not familiar with what that is, it's relatively straightforward. The photon density is so high that they strengthen gravity through the stress energy tensor. And the effect is minute. It's about a 0.1% effect, but that core all the time is sitting on a very soft equation of state. It's got a gamma of about 4/3. And it only takes a nudge to push it over the edge to begin to collapse. And so it does with the effect of GR. And as the core contracts, it heats up, produces more photons, more and more correction to gravity. It's a slow roll instability to collapse of the core. And in almost all cases, the core is just thought to collapse to a black hole of a few 10 to the 4 to a few 10 to the 5 solar masses. And what numerical simulation... I'm going to avoid that corner. So what numerical simulations show is that for a wide range of accretion rates, you get a fairly narrow final range of direct collapse black hole masses. So between about 0.01 solar masses per year and even 10 solar masses per year, the final mass of the star and the black hole it collapses to, it only ranges from about 10 to the 5 solar masses to about 3 times 10 to the 5 solar masses. So we think that GR instability tends to impose this characteristic mass on early quasar seeds. So really briefly, I discussed that these were bright. And what are the prospects for detection? Well, when we calculate their spectra, we can't just calculate the spectrum of the star, redshift it, cosmologically dim it, and then convolve it with filters to figure out what the AB magnitudes today would be. We have to take into account that dense, hot accretion shroud that grows the star in the first place. And it turns out that rather than obscuring the star, that shroud actually can enhance its near-infrared luminosity by a factor of maybe 2 to 5 for stars that are between 10 and redshifts between 10 and 20. That's simply because the atomic envelope, reprocesses high-energy photons from the star. into wavelengths that are just redward of the Lyman limit in the frame of the star. And then those are redshifted in the near-infrared today. And so here's an example of that enhancement that I'm talking about. And so what we find is that these stars, they have typical near-infrared magnitudes and near-cam bands of about 29 to 30 from redshift 6 out to about 15. So we could predict nominal detections by JWST, but JWST would have to come across one. At redshift 6, they are just barely bright enough to appear in proposed W-FIRST surveys. That could be a very different picture because W-FIRST surveys will be wide field, and they would detect these stars at a redshift at which their formation rates are predicted to peak. So I would say that there is a good possibility if W-FIRST goes up that it could come across some of these supermassive primordial star candidates, which could then be followed up very nicely with James Webb. So now, I'm going to skip that. I would say, so it's important to remember that massive seed formation is a necessary but not sufficient condition for the formation of a quasar. After formation, that seed has to be rapidly and consistently fed by either a series of mergers with other gas-rich halos, which has been examined in a number of simulations, or rapid feeding through these cold accretion flows. And so we studied the rapid growth of a quasar, a direct collapsed black hole, in cold accretion streams in the ENSO cosmology code. So what we did was we went through a bunch of 50 megaparsec boxes until we found a halo that reached 1 trillion solar masses by redshift 7 without having been the product of more than one or two major mergers. In other words, it was mostly the product of rapid accretion. And then what we did was when that halo, passed the threshold for atomic cooling, we seeded it with a 10 to the 5 solar mass direct collapsed black hole, turned on X-rays from the black hole, which we can couple to both hydrodynamics and chemistry in ENSO. And then within the host galaxy of that black hole, we activated star formation. And with star formation, we have winds and their metals. We have their ionizing UV radiation, which we transport with the Moray radiation transport package. And we also include their supernova explosions. And so we have up to about 10 levels of refinement. It gives us a resolution of about 30 parsecs. And we, instead of using the Bondi-Hoyle accretion, since we don't resolve the accretion disk around the black hole, it's on the parsec scale, and we only get down to 30 parsecs, we adopt an alpha disk model for accretion that takes into account approximately angular momentum transport. And so, and the X-rays we used were 1 keV photons. And so what I'm showing here is just the progression in size of the H2 region of the quasar. At redshift, we turn on the black hole at redshift 19. At redshift 17, it's still tiny, the H2 region is. Still pretty small at redshift 9.5. But then by redshift 7, it grows to 2 megaparsecs in radius. And what you're seeing there is simply the consequence of exponential growth of the black hole under this constant heavy feeding of gas by accretion flows. So the black hole in our model goes right through the center of the error bars for the Mortlock quasar at redshift 7.1 in that case. And it falls a bit above the Bañados et al. Black hole mass at redshift 7.5. So that gave us basic confidence that we didn't have the physics too badly off. Then when we looked at star formation rates in the host halo of the quasar, at redshift 7.1, we're at about 250 solar masses per year, which is in agreement with the error bar set on the star formation rate in the host galaxy of the Mortlock quasar, most recently by ALMA, by Venemans et al., back just last year, I think. So that gave us confidence our basic prescriptions for star formation feedback and X-rays were working. But really quickly, in my last couple of slides, 2 slides, here's the H2 region of the quasar, and you probably can't see them from where you're sitting, but there are these really bright yellow flecks throughout here. That's supernova heating. And the spherically average temperature profile of the black hole shows that the H2 region does go out to about 2 megaparsecs. And then metal production. So one of the things that we find, because we get these very strong starbursts, is that the host galaxy is already solar metallicity by redshift 7.1 and supersolar at its center, which also is in agreement with observations of the Mortlock quasar. And let me briefly, finally, talk about detectability. So because we created H2 regions, we are able to spherically average them and then calculate their near-infrared luminosities today with the cloudy code. And what we find is that these objects will be visible to Euclid and W-FIRST out to redshift 15, only after 15 because their H-band filters get cut off by the Lyman limit above redshift 15. So for those wide field surveys, they won't be able to find objects at higher redshifts than that. But this is really interesting and exciting because Euclid and W-FIRST will open up this new era, I think, of quasar astronomy from redshift 5 to 15. And candidates that it discovers could be followed up by JWST and much better spectroscopy to study them in much more detail. So there's a lot more work to be done, but let me just make a final statement. When we're modeling primordial quasars, we really have to have the primordial physics right. And X-rays from the black hole actually trigger primordial star formation in the host galaxy because of secondary ionizations due to the X-rays promoting H2 formation through the H- pathway. And then when the ionizing radiation and winds fire up from those stars, they perturb flows onto the black hole. So these are interlocking feedback procedures or processes that you have to capture from the earliest stages. And so I think we're at the point where we have that physics in the simulations and we can do a lot of really interesting studies. So thank you very much.
Thank you. We have time for one question. Go ahead.
How does the black hole accretion rate trace the star formation?
So really quickly, at redshift 7, why don't I say what the total stellar mass is in the galaxy at redshift 7.1? It's about 1.5, the halo mass. So we think that we've got basically the star formation right, but do these, for example, fall on kind of an M sigma relationship? They're off it. So at high redshifts, interesting things happen. It's transient, and we need to do a lot of study, and we need to get more of these. I mean, the difficulty is studying the stellar populations of the galaxies and getting that data because they're just so hard to see at above redshift 6.
How many of these quasars are at Z larger than 7 do you expect in W-FIRST and Euclid?
So we don't know because we don't know what the formation rates are yet. So at redshift 6, we're roughly at 1 per cubic gigaparsec. I think that they're talking about several tens of quasars, at least between redshift 6 and redshift 7. Or maybe, no, or redshift 7, excuse me, and redshift 8 with the wide fields. So
Using the blue prism, or just
I'm sorry?
using the blue prism or in Euclid or?
Yes,
Yeah,
I think
okay.
so.
Thank you very much. Let's thank Daniel again.